Okay, so today I will present two research works on prefabrication supply chain at University of Washington Lean Construction Research Lab. And in this presentation, I want to discuss what supply chain management is about and address two different approaches that we are working on at University of Washington Lean Construction Research Group. One on rebate calculation, and the other one is about production scheduling using a dispatch room. So first agenda is what is supply chain management? Supply chain management is a practice of working collaboratively in a network of interrelated processes to best satisfy end customer needs while rewarding all members of a chain. Easy to say and hard to do, right? So that's our agenda. Since we are talking about supply chain management in off-site construction project, in the beginning of this talk, we need to narrow down the scope of off-site construction that the research is applied. The categorization graph you see now is the one developed by McKinsey Consulting last year, defined by module size and system complexity. In our study, we assume that modules are componentized module such as a electrical switchgear, or panelized modular such as precast concrete wall or cotton wall. In both cases, each order should be coordinated between a supplier and a contractor. Last year, I had a chance to have an extensive case studies on offsite construction projects, which I found reliable and economic supply chain is critical at offsite construction projects. However, I also found several critical issues related to supply chain coordination. Generally speaking, a contractor should determine delivery due taking into account their schedule, when to install the module. Suppose this density function that you see the graph represents when to install from the contractor's perspective. A contractor determines TD, a time to deliver or delivery due. However, depending on their actual progress on site, contractor can change TD to actual T. Contractually, however, most commercial contracts do not charge on order variability, the changes of delivery due after order is made. Those delivery due changes mostly come from contractors' lack of plan reliability. Such order variability leads to increased inventory cost or contractors' delay cost. Since the risk on order variability are transferred to a supplier's contractually, it does not motivate contractor to improve plan reliability. This is a story that motivates our research. Our first approach is to use contractual mechanism. Suppose a supplier and a contractor work independently, working for its own profits, not considering others. How can we motivate each to work toward total supply chain cost minimization? As you see in a diagram, a contractor determines quantity and delivery time TD, while supplier provides price information. A supplier can choose either uniform pricing, the same unit price for all orders, or rebate, which gives incentives for the orders without changes. And as you see the graph of the function, the contractor determines when to install the delivery due TD. If a contractor goes with uniform pricing, which is the most case, a contractor's cost should include contractor's price P and the contractor's delay cost when they need a product earlier than TD. This equation does not include inventory cost because a supplier is responsible for inventory cost. If you take the derivative of this equation to get the minimum value of CC, An optimal TD should be always possible installation date. In other words, the contractor schedules delivery due at the earliest possible date, regardless of the probability distribution of actual requirement time. However, we want minimum total supply chain cost, not minimum contractor's cost. To calculate the total supply chain cost, we develop a cost equation considering not only supplier's cost, but also contractor's cost. This equation, in this case, includes supplier's inventory cost as well as a contractor's delay cost. However, this equation assumes the integrated supply chain in which a contractor and a supplier are fully coordinated and work toward a shared goal. If you take the derivative of the equation, cost equation, to get the minimum value, you would find that optimal delivery due, which gives you the minimum total cost, is inverse function of antiderivative of F when inventory unit cost over sum of inventory unit cost and delay unit cost. But here's the problem. The problem is, why does the contractor choose delivery due like that? Because it does not give me my minimum cost, right? Why should I consider supplier's cost as well? Therefore, we should devise a way to motivate a contractor to behave like that in a integrated supply chain, even in a decentralized supply chain. So we set a rebate delta and rebate to a contractor when a contractor does not change order delivery due. Then we develop a contractor's cost equation and take the derivative. Then we get the amount of the rebate as shown in the screen. Therefore, when supplier is aware of distribution information on when to install T density function, then a supplier can determine the amount of rebate to work as integrated supply chain. Okay. So what is new and why is it important research? In this research, we take order variability as a function with distribution. We also develop a contractual tool to motivate a contractor to reduce plan variability. Now we are developing a case study in different distribution scenarios. Okay. Then the other approach, the second approach to this same issue is production approach, not contractual approach. In this research, we want to develop a tool for production scheduling to have minimum impact of order variability. For this approach, we have used several techniques. We have used optimization technique, we have used dispatching rule, we have used recently machine learning, especially Q-learning technique. Today, I want to share one of our research work, a research with dispatching rule. Most small fabricators should develop a schedule in a way to minimize their resources. However, many small fabricators have limited resources, not enough to develop robust scheduling or optimization responding to order variability. So they should use dispatching rules in practice in most cases because of their simplicity. There are three popular rules in the industry. The first and the most popular rule is EDD, early due date. Under EDD rule, a production system chooses the next job having earliest due. The second rule is SPT, shortest processing time, which chooses the next job having the shortest processing time. The next one is critical ratio, in which next job is chosen considering the available time divided by the total remaining processing time of the job. These three, they are all popular among fabricators, but EDD rule is the most prevalent rule in the industry. However, all of them do not take into account the order variability, which changes due date of orders due to lack of plan variability of plan reliability of contractors. So to consider a contractor's order variability that is related to his planning reliability, we propose a new rule of EDLU, early due and low uncertainty. In a new rule, we shift the risk of production disruption to a contractor who frequently changes the delivery order. Therefore, order with high due date uncertainty starts late. In other words, a proposed rule incentivizes a contractor to increase their order reliability. To test our proposed rule, we developed an algorithm called DPPSM, Dynamic Prefab Product Scheduling Model. DPPSM consists of two parts. The first part is a due date uncertainty generator. The second part is production scheduling system. In our simulation experiments, we made several assumptions in our scenario. There were total 15 orders. Each order has different level of order variability. For example, job number 5 has more order variability than job number 1 or 2. And we run the simulation and see in each case which schedule algorithm gives best result. This table shows the result, and the table shows EDLU, our proposed rule, gives better performance in most of scenarios. The next best one is EDD, but in case of scenarios with tight due date between orders, SPT was the best rule, showing the lowest tardiness. In light of lean construction principles, the simulation results suggest two issues. The first one is order variability leads to variance of prefabricated product delivery. The EDLU rule is more effective than traditional rules when order variability increases. It also motivates a contractor to improve his plan reliability, such as PPC or PCR. And finally, this study assumed the due date uncertainty has the uniform distribution. We will conduct the further study to verify the effectiveness of the proposed model with the distribution shape of uncertainty from actual construction project, and we are working on that now. Okay, so in today's presentation, I showed you two different approaches to managing supply chain in which order variability is critical in coordination. A rebate method is from contractual perspective, and a scheduling method is from production perspective. In both cases, it is critical to measure and study the function of order variability to advance our industry. Okay, that's it. So thank you for attending and listening to my presentation. If you have any question or interest in working with our group on these subjects, please contact me. Thank you.